Okay, so what this graph is showing us is, so essentially the X and Y axis. So the Y axis is the boiling point of certain molecules. Okay, so obviously the higher this goes, the higher the boiling point. Or think of this as the stronger the attraction, right? As you go to the right on the x-axis, you have the size of the molecule, the molecular mass or weight, becoming heavier and heavier. So look at the molecules that are here. So they're all hydrocarbons, so meaning they're made up of hydrogen and carbons only. So here you have the smallest type of hydrocarbon, methane. So methane's boiling point is relatively weak, and actually at room temperature, it is a gas. Ethane, which we don't, so I don't expect you to know the names of these molecules, but anyways, so as you can see, we're getting larger. The boiling point is going up, and it continues to go up. So actually, it gets to the point where octane, which is what this is now a liquid at room temperature. Octane is one of the main kind of ingredients in gasoline. So what happens is the attraction between these particles, the LDF is increasing, the attraction is increasing. So what happens is the particles came so close together that it eventually became a liquid. And what happens is if this hydrocarbon continues to go higher and higher, it can become a solid. So for example, wax is basically a hydrocarbon that is in large, very large groups of hydrocarbons. And because it's so large, the LDF is so high, the attraction is now so that the particles are close enough together to become a solid. So intermolecular forces really dictate the properties that you see when you're talking about different molecules. So sometimes when you're looking at a term, this comes up in your textbook as well, van der Waals. Van der Waals is really a combination of two different forces of attraction, so LDF and dipole-dipole. You don't have to use this term. You should know what the term means, but I'm okay with you using the three that we are learning how to use, right? So you have hydrogen bonding, we have dipole-dipole, and LDF. So LDF is in all molecules. Dipole-dipole is only in polar. And hydrogen bond is polar, but it must have one of the three types of special dipoles. Now, when you're looking at a molecule, you can have more than one intermolecular force. So for example, let's look at water. Water's polar. So water has hydrogen bonding because it has an OH group. It has dipole-dipole because it's polar, right? We can see the dipole actually. And it has London dispersion forces because it has electrons and protons. So you can have a molecule that has all three. Let's say we had carbon dioxide. Okay, so carbon dioxide is symmetrical, it's nonpolar. So it does not have hydrogen bonding, right? There's no OH, NH, or FH. It does not have dipole-dipole because it's not polar. So the only thing it has is LDF. So it might have one force, it might have two forces, it might have all three forces. You have to think, what criteria here does it have?